Today's topic for discussion is how to define RSD limit for precision. The precision is one of the important parameter when it comes to analytical method validation. And you may be conducting validation for different tests like assay or related substances, and the limit for the precision, which can be expressed in terms of RSD, can remain same or can it vary with the test. So that is the point of discussion. And let us first understand what is the reference I am going to take in defining the RSC limit for the precision. So this is the reference guideline that I am going to consider while defining the RSC limit for precision. AOAC guideline for single laboratory validation of chemical methods for dietary supplements and botanicals. So you must know that according to the various guidelines like ICH, NVISA, EURACHEM, AOAC, and many more, the definition of precision is very much defined. And you can refer the definitions onto the screen. And if you understand that all these guidelines says that the precision can be expressed by percent RSD or standard deviation. But the next important question you must have, how to define the limit for percent RST. If I have to say that my method is precise, I must understand first the acceptance criteria for the RST. But the problem is ICH, NVISA, EURACHEM, EMA. Now these regulators or guidelines about their method validation does not talk about the specific RSD criteria to confirm whether the method is precise or method is imprecise. But fortunately, the AOAC guideline for analytical method validation has provided a very interesting reference for calculation of the RSD during the precision. So where from the reference come? And the reference comes from the Horwitz equation. Now this is the equation that we are going to discuss, which is going to help us in defining the RSD limit for the precision. So what is the Horwitz equation and what it says? So in the year 1980s, Horwitz et al. Has published a equation which has the relationship between the precision of analytical method and the concentration of your analyte. So what is that Horwitz equation, and here it is. So the predicted RST is equal to C raised to minus 0.15. So whatever value that you are going to get, that is in terms of the percent. Let us now understand what is the meaning of RSDR and the C. So RSDR is nothing but the relative standard deviation or coefficient of variation under the reproducibility conditions, or you can also refer to as a repeatability conditions, which we generally perform during the precision study. And what is the meaning of C? It is the concentration of the analyte expressed as dimensionless mass fraction. Now these last three words are very important. Dimensionless mass fraction. So let us understand, first how to determine the dimensionless mass fraction. So if you go back and look at the equation, we need to have only the concentration of the analyte. And based on to that, the Horwitz has given the equation to predict the requirement of the percent RST. So let us understand how to determine the dimensionless mass fraction. The mass fraction is the amount of mass of one substance divided by the mass of the total mixture. That is the mass fraction. and the sum of all the mass fractions is always equal to 1. Let us take an example over here, the mass by mass. So the mass by mass will cancel each other and result into a dimensionless mass fraction or a unitless fraction, like milligram divided by milligram will result into a unitless quantity, or gram divided by gram, it result into a unitless quantity. So let us say that you have to perform the precision for an API. I mean the precision for the assay of an API. So generally, ideally, the content of API into the sample will be 100%. So how you are going to define the dimensionless mass fraction? So 100 gram of the API is containing into the 100 gram of the given sample. So 100 divided by 100 becomes 1. So for any sample with the potency of 100% has the dimensionless mass fraction equal to 1. Let us take the another example. You have an impurity with the limit of 1%. So what is the content of impurity in the given sample? If you assume that the sample content, if you assume that there is 100 gram of the sample, then that 100 gram of the sample will contain 1 gram of the impurity. So 1 divided by 100 becomes 0.01. So 0.01 becomes the dimensionless mass fraction for 1% of the impurity. Let us take one more example. Impurity with the limit of 10 ppm. So what is the definition of 10 ppm? The content of substance into a 10 raised to 6 part of the given sample. So with the 10 ppm, you can easily understand that the 10 gram of the impurity must present in the 10 raised to 6 gram of the sample. So if you further simplify these terms, you will end up with the 0.00001, which is the dimensionless mass fraction for the 10 ppm. I hope you understand how to calculate dimensionless mass fraction. Now, once you understand this, now let us understand how this RSD can be calculated for the different concentrations. And for that reason, I need to bring the Excel sheet in the presentation. So here is the Excel sheet now, and I hope you can able to see the Excel sheet. So I have taken the example. You can see here, example is as such API or the tablet containing 10% API, impurity with 1% limit, with 0.1% limit, the impurity with 100 ppm limit, 10 ppm limit, 1 ppm limit, 100 ppb limit, and the 10 ppb. I have just taken this various examples so that you can relate this calculation with the different scenarios. So what is the second step? The concentration. So what is the concentration for an API into a given API sample? It is going to be 100%. So what is the concentration of the tablet API containing the 10% of the API? It becomes 10. Impurity limit with 1% is going to become 1, and rest you can understand. Now the next important step is calculating the fractionless mass concentration, m by m. So I hope you remember that how you done in the just one slide before. So 100 by 100 going to become 1. 10 by 100 for 10% is going to become 0.1. Similarly, the mass fraction for 1% impurity is 0.01. For 0.1% impurity, it is 0.001. Similarly, for 10 ppm, it is going to become 0.0001 and so on. I hope you can relate with this calculation. If not, you can go back to the video and understand how this mass fraction has been calculated. Now, having calculated the mass fraction, the next step is to calculate the predicted percent RSD or P percent RSD, and this R can stand for maybe the repeatability or the reproducibility. So how to calculate that? The calculation formula is C raised to minus 0.15. So with respect to as such API where the concentration is expected to be 100%, the predicted RSD is 1%. For 10 percentage of the substance, it is 1.4. For 1 percentage of the substance, it is 2.0. Let me show you where this calculation formula has been taken, and for that reason I need to bring the AOAC validation guideline. So let me go to the relevant page. Yes, I think we are on the relevant page now. The point number 3.4.2, repeatability precision, and this is the calculation formula, which is just highlighted with the yellow color. RSDR is equal to C raised to minus 0.15. And you can see the similar calculations over here. RSDR is equal to C raised to minus 0.15, and these are the RSD requirement now. The predicted percent RSD across the different concentration ranging from 100% to 10 ppb. Now the next point is very important that I have given as the limit range. So from where this limit range has been derived? So for that reason again I need to bring back to the guideline. Now on to the page number 22. This particular paragraph is very important. So what this paragraph says, the acceptable values for repeatabilities are between 1/2 and 2 times the calculated values. So whatever RSD values I calculated, that is not the final limit. That is the ideal limit. But the range can be zero point 0.5 to 2 times of the defined predicted RSD. I hope you understand. And when I go back over here, then you can see that the zero point 0.5 of the predicted RSD and 2 times the predicted RSD. Now whatever here you see into the selected text is the ideal value for the RSD. But it can be 0 0.5 times of ideal value, or it can be 2 times of the ideal values. So the 0.5 times will become 0.5% because my ideal value of RSD is 1%. However, the 2 times of the predicted RSD value will become 2%. So you can easily understand that for an assay of API where the concentration of the substance is 100%, the limit range for RSD from the 0.5 to 2%. In case if the concentration of the substance or analyte in the given sample is 10%, the limit range for predicted RSD is 0.7 to 2.8%. And you can understand the rest of the limit ranges according to the concentration. Let us go back to the presentation now. So same concentration values and their expected RSD values are tabulated for your easy reference, the minimum and the maximum. Now you may be having the question how to define the requirement for the percent RSD, because we never have the range given for the percent RSD under the precision study. So let us talk about that point also in the upcoming few of the slides. Let us understand the conclusion now. The RSD is only dependent on to the concentration. So if you look at the Horwitz equation, it has only one varied parameter, that is the concentration. So according to his assumption that the RSD is only dependent onto the concentration and it is not dependent onto the nature of the analyte, the test material or the analytical test method or the technique. RSD increases as the concentration of the analyte decreases. And the fourth point is very important, that the RSD criteria must be defined as per the need of testing and your specification range. And I have given the example of assay limit of an API in case if it is 99 to 101% versus 99, 98 to 102%. So which assay limit is stringent? Of course, the first one, that is 99 to 101%. The second acceptance criteria for the assay is 98 to 102% is quite relaxed. Now, if you go back and check the predicted RSD requirement for the 100% concentration is from zero point 0.5 to 2, zero point 0.5 to 2. So it can be as low as 0.5% and as high as 2%. So I have a question for you. What is the acceptance criteria you can define for 98 to 102% assay specification? The 2% can fit over here. But can the 2% RSD fit good for 99 to 101% assay specification? May not. And for that reason, you can have the stringent acceptance criteria like the percent RSD not more than 1%. So this is the meaning of the fourth important point. So I hope you now have some clarity and reference to understand and define the RSD limit for precision study. Thank you so much.